Hello students, welcome to another lecture. Today we are going to discuss number of particles in a mixture. Okay, so suppose you have a mixture of, right, you have different particle sizes. Okay, you have a mixture. Okay, so I want to find number of particles in this mixture. Okay, for a particular size. Remember, this all are a mixture in a one container, single container. Okay, so I want to find the number of particles in this fraction, in this fraction, in this fraction. I already discussed how to find the number of particles for a given fraction. Let's example, for example, take this sample. Let's say the mass is m. Okay, so what are the number of particles? So we already discussed in previous, the number of particles is nothing but, okay, volume of all the particles in this mixture divided by volume of each particle, single particle. Okay, so how to find the total volume of this mixture? That is simply your what, mass of that sample divided by density, right? Since the density of each particle will be same as the other, so I can replace this by m by rho p, and here this is the volume of each particle. Fine. So this is the, so you can rearrange it. So you will get mass of that sample by rho p and vp. Fine. Okay. So now you can express volume of a particle as a is directly proportional to the diameter of the uh, cube of the diameter. Okay, it is directly proportional to the cube of the diameter of the particle. We are talking about the single particle. Okay, now to remove this proportionality constant, we can write Vp is equal to a dp cube. Okay, this is what is given here, and this a is called volume shape factor. Fine, this is called volume shape factor. Now using this relation, I can find out the number of particles in a given mixture. So move on to this slide. Okay, so now instead of Vp, I can write Vp in terms of the volume shape factor. What is that? M by rho p as given, and Vp is nothing but a diameter of the particle cube. Fine, this is. Now if we divide, this is the mass of the sample. Okay, total mass of the sample. So if you divide by total mass on the both sides, then what we'll get? N by m equal to 1 by rho p a dp cube. Fine. So this n by m is called nw. Okay, this is nothing but number of particles per unit mass. Okay, nw is number of particles per unit mass. Okay, so this is the formula for when we'll take a single sample. We'll take only this sample. This has uniform diameters throughout this and the mass m. Okay, then this formula is applicable. What about if I mix a lot of samples. Let's say M1, this sample of diameter dp1. Okay, and here it is, let's say M2, this one, this part is M2, and with average particle diameter dp2. Similarly here M3 and dp3, and so on, dot dot dot, up to mn and dpn. Okay, now what happens in this case, we can write the number of particles formula like this: m1, total number of particles in this mixture. So m1 by what? Rho p a, then dp cube. We're talking about sample 1, so dp1 again, plus m2 by rho p a dp2. This is this. So we have rho p a dp2 cube, right, and so on. Okay, see, density of the particles will be same in all the samples. Again, volume safe factor will be also be same in all these samples. Okay, only the average particle diameter will be different, and the mass of each mass of that each sample will be different. Total mass will be different. Right? Now, just divide by the total mass. In this case, total mass will be total mass of the mixture. So, by dividing, let's say m is the total mass of the mixture. Okay. So, if you divide by m on the both sides, then you'll get m, and by m is equal to, you'll get m1 by m rho p a dp cube, right, and so on. M2 by m rho p a dp2 cube, like that. Now, what is this? Mass of a sample divided by total mass is nothing but mass fraction. So I will represent it as x1. Similarly, here it will be x2, m2 by m, and so on. So this is nothing but number of particles per unit mass of the mixture. So I will write it NW. So this is going to be equal to, so x1 plus x2, right, by dp1 cube dp2 cube, and you can take out the common factors like rho p a rho p, right, and if you write this in summation notation, it is nothing but a by rho p summation I is equal to, from sample 1 to as many samples as possible, and xi by dpi cube. This is the formula for number of particles in a mixture of different average particle diameters. Okay. Okay, next. And also, so this is what we just derived, right? And you can replace this by 1 by dv cube. What is dv? This is volume mean diameter. We already calculated in the last class. See here, this, sorry, see, you can see here this, right? So if you take cube root on both sides, then this will become cube and this will become 1. So you can see it is inversely. So you can replace here xi dp cube will be 1 by dB cube, right? So you can remember this formula as well. This is a shortcut to remember. If you know the volume mean diameter, then you can easily calculate number of particles per unit mass. Okay. Okay. Now next we'll learn screen analysis. What is screen analysis? We'll see. And what is standard screens? Okay. Let's move on to this. Okay. You can go through the PDF later on to understand more. Okay. In screen analysis, what we do is, suppose we have a mixture of different average particle diameters. Okay. We'll want to separate this mixture into different samples. Like I want to separate into DP1 average diameter. I want to separate into DP2 average diameter. Okay. So we have different particles of different sizes. It's a mixture, right? I want to separate this into like this. I want to separate into different particle samples. Okay. I want to separate into this. So what is the best way? The best way is by screening. You already do at homes, right? Using something like T strainer. Yeah? So you already do at home. So what we'll do, we'll see is what is happening in the industrial level, what the industry does to achieve this mixture separation. Okay. So to use this, we use screens. So screens, how these screens look like is, suppose, okay, I have different screens here. This is the side view. Okay. And if you see the top view here, so it is nothing but a circular. It can be rectangular also, and it doesn't matter. So inside these screens, we have like this mesh. We have mesh. Okay. So the first one will be the larger. The next one will be little bit smaller than the previous one, and smaller. The size decreases. Okay. So what happens if you put this mixture here on the top, then shake a little bit, then what will happen? The bigger particle sizes will be here, right? And the smaller particle will pass through the next screen. So on the next screen, again the smaller diameter will be trapped here. Okay, again the smaller than this will be trapped here, and so on. At last we keep a pen here. Pen means just a pen. It doesn't have any pores. So I just simply collect the smallest particle size here. Okay. So these are called standard screens. Okay. And this is pen. And this process is called screen analysis. Okay. So if you see this table on the left side, so for each for for each screen we have denoted a fixed number. Let's say this is a mesh of 4. Okay, this is mesh 6. It will be in increasing order. So these are standard mesh numbers. If you can easily find out on net or on a standard uh, chart that mesh number 4 will be having the opening of this diameter of the screen will be this opening will be this one. So it is given here. Okay. Again, the mesh size of 6 will be having a smaller than this, because I told you, right, the topmost will be having the largest opening, and as you move down you will have a smaller and smaller opening, but the mesh number will be increasing, right? As you increase the mesh number, then the diameter of the opening will be decreasing. Fine. So it has some kind of inverse relationship. Fine. Okay. The one of the things you should know is, what about, let's say this is the topmost mesh. Let's say mesh number 4, then you have 6. You know, the opening of this will be something like this. Let's say it is DP1. For now, let's say DP1 or DP4, right? DP4. And the mesh opening diameter will be, let's say, DP6 of mesh number. This is mesh number. Okay. Okay, this is 6. So what is the relationship between the size of the openings of between these two? So for standard, we say standard Tyler series. Okay, this is Tyler series is for the screen, standard screens. Okay, so what is the relationship between these two? So let's say the area of this opening is, let's say, A4, right? And the area of this opening is A6. Okay, what is the relationship between these two areas? So for standard Tyler series, it is, so the, the mesh number 4 is the larger one, right? The opening is large compared to this is smaller. So A6 opening is less than area of the mesh 4, right? Okay, so what is the relation between these two according to standard Tyler series? So according to this, the A4 is, top one is 2 times of the smaller one, the next one in the series. Okay, 2 times of the area. And this is a mesh, so this is kind of square, right? So what is the area in terms of the diameter of the opening? So it will be x square, right? What is the area of square? X square. So in this case it will be dp square. So for the A4 we have dp4, sorry, dp4 square, and for the A6 we have dp6 square, right? And we have 2 factor here. So now if you simplify it, you'll get dp4 is equal to square root of dp6. Fine, this is what you should remember. Okay, so in exam, the one question might be like this: that what is the relationship between the diameter of the uh, mesh size with the preceding mesh size, or the next mesh size in standard Tyler series? So you should answer square root 2, or you can say it is, if you rearrange it, you can say dp6 is equal to 1 by root 2 of dp4. Okay, so the smaller is 1 by root 2 times of the larger one in the series. Okay, see, this is only true for this series. We have mass 4, 6, 8, right? The relationship between these two is square root 2. The relationship between these two is square root 2. The relationship between this and this will be what? Just multiply it. It will be 2 times. Okay, so you just remember this. Okay, next we'll be discussing the size analysis. I already told you there are two different types of size analysis. One is differential and one is cumulative. Okay, so how to plot the graphs? So let's solve this. So here on the first column we have mesh numbers. Okay, 4, 6. This is the standard styler series, and the screen opening. The screen opening is the mesh 4. That is the mesh. Okay, this opening is 4.699. Similarly, for 6, mesh number 6 is this 3.2327 millimeter. Okay, and so on. And suppose you want to separate a mixture of samples using screen analysis. So first you will put the mixture on the top, right, on the mesh 4, right? Then you will shake a little bit, then the smaller particles come through and it will land on the 6. Again the smaller particles will land on the 8 again, and so on, and lastly it will be get collected on the pen. The particle which it gets collected on the pen will be the smallest of size. It will be very fine particle. Okay, so let's say the mass fraction is given. Okay, so on the first mesh, on the first screen, it is 0, because it is assumed that there is no particle collected or retained on the mesh 4, so it is 0. Okay, then on the next 6, some particles have retained on the mesh 6, so it is 0.0251. This is the mass fraction. Okay, so if you ask me how to calculate the mass fraction, so you can simply use weighing balance to calculate the mass fraction. How? So firstly you have a mixture of particles, right? You just weigh the total mass. Okay, then you do the screen analysis. You just put the whole mixture on the top and shake it, and after the shaking process, the particles will be collected on different mesh according to their sizes, right? So just collect the sample from the different meshes. Let's say I have collected the sample from the mesh number 6. Just weigh it. So now you know the mass of the samples collected, mass of the mixture particles collected on the mesh number 6. So you can easily evaluate the mass fraction. That will be definitely the mass on the mesh number 6 divided by the total mass. Okay, so you can find out the mass fraction. So this is true for the each mesh sizes. Okay, so you can calculate the mass fraction. And now what is the average particle diameter in the increment? So what we are talking about is, so we have this mesh 4, let's say mesh 4, and we have mesh 6, right? So the particles which are just equal to this opening, will pass it through it, right? Okay, so the actual average particle size will be the average of these two openings, because it will be having the particle size which is exactly same as the opening size of the mesh 4 will be just passed through it, and right, so and it will be retained on this. Okay, so we have to exactly find out the average particle in this increment. So in this increment, if you are moving from mesh 4 to mesh 6, then the average particle diameter will not be equal to simply this. It will be the average of these two openings. Okay, so since we have mesh 4 and there is no mesh above it, so there is no average here, right? So it will be simply, you cannot calculate average, so it is left blank. Okay, so but as we come along, then the average will be 4.013 between these two. This plus this divided by 2. Again, next average diameter in the increment will be this plus this divided by 2. It will decrease. Okay. And what about cumulative fraction smaller than dpi? Okay, smaller than. What do you mean smaller than? Okay, this will be basically between 0 to 1. So 1 means what? Smaller than 1. See, all the particles have passed through this mass 4. There is no particles left on the mass 4. So the mass fraction which is smaller than this opening is 1, right? All the particles have passed through this size, right? So cumulative mass fraction smaller than dpi will be 1 because all the particles have passed through it. None of the particles are retained on this mesh, so there is 1. And what about the mesh 6? So in mesh 6 we have retained some fraction, right? 0.0251. So less than this diameter is this 1 minus this, right? So this is nothing but 1 minus 0.0251 because we are talking about smaller than. So if the particle is smaller than this diameter, just pass through it. Okay, only this fraction retained on the mesh. So the remaining particle which pass through it will be 1 minus this, and so on. And lastly, you will get 0 because all the particles are collected on the pen. There is no particle which passes through the pen. Okay. Now, if you plot this data, you get something like this. So here, if you plot particle size dp, we're talking about average particle size, and the mass fraction. So in this table, between these two, you'll get something like that, this kind of graph. Okay, so this is kind of histogram. So this is called differential analysis. Okay, this is called differential analysis, screen analysis. Okay. Okay, next we have cumulative screen analysis. I already told you about that. So you simply plot it between these two columns. So if you plot this column and this column, so this will be on x-axis, this will be on y-axis. So you'll get the cumulative screen analysis, this graph. You can try out this plot in Excel. Okay, if you know MATLAB, you can plot in MATLAB. Okay. Okay, next we have a problem here. So example 28.1. So try to go through this problem and solve it. Okay, so the question states like that: the density of the particle, the density rho of the particle is given. This is given, or in both units, kg per meter cube as well gram per millimeter cube, and the shape factor a is given as 2, and phi s, that is sphericity, is given as 0.571, right, for the material between 4 mass and 200 mass in the particle size. So 4 and 200 mass, you have to go through the table again. Yeah, it is saying that for the material from 4 to 200 excluding pen. So you have to calculate what? First thing, you have to calculate AW. AW is what? Specific surface area, right? Total surface area divided by the total mass, right? So you can easily calculate it, but remember the unit is in millimeters, square millimeters per gram. So since the density is given in both units, so you can use this one. Okay, you can easily calculate it. But remember, AW is the summation of all the mass fractions, okay, from 4 mesh to 200 mesh. And next you have to find NW. I already told you the formula, okay. Next you have to calculate volume mean diameter, then surface mean diameter ds, then mass mean diameter, then Ni for 1500, 150 and 200 mesh. So you just calculate Ni for 150 to 200 mesh increment. That means if you see the table, so 150 to 200. So here 150 and 200. So it is written as like this: 150 by 200. That means the mixture has passed through 150 mesh size and got written in 200. What is the increment in this? So what is the increment? You can find it here. Okay, this one. Okay, this is the, so you use these values to calculate the Ni, number of particles in that increment. You know the formula. Okay, so just go through it. Just do try to do it uh, using table. Just don't simply put the values. Make a table and put the values, calculate xi by dpi and do the summation. Okay, and so do it as a homework. Okay, this will be your homework, and upload it on the Google Drive. So I will give you the link for the submission of this. Okay, I will post it on the Google Classroom. Just write solve this problem. Okay, just simply don't copy this thing. You have to show the stepwise. Okay, for example, suppose you want to calculate the AW, right? So you know the formula, so you have to do it like this. So you have 4 mass, 6 mass, 8 mass, right? So what is the mass fraction? From the table you write it here. Then what is the dpi? You from the table you can write it here. Now calculate xi by dpi here. Then at the end just sum this up. You will get the summation dpi, this formula. Now put this value in this equation, you'll get it. So simply do it for all other problems. Okay, so similarly, while calculating volume, surface, volume mean diameter, surface mean diameter, use a table. So okay, so do it as a homework. This is your first assignment. So one, so do it. So I will provide you a link on the Google Classroom so that you can upload it. Okay, the deadline will be notified soon. Okay, thank you.